Hey everyone. In the last video we talked about the conformations of alkanes that can be formed through the rotation around single bonds. We talked about staggered and eclipse conformations, and for the staggered conformations we talked about the possibility of anti and gauche conformations. And then we learned how to rank those in relative energies. We're going to move on now from alkanes to cycloalkanes. So this is when we take an alkane and make it into a ring. We're going to learn how to do the naming, and we are going to then talk a little bit about types of strain that are generated in cyclic structures. So how do we make a cycloalkane? Right? So if we want to start with an alkane and make a ring out of it. So let's kind of go through a little paper exercise here. So I'm going to draw a hexane. So I'm going to just put methyl groups on the ends. So this is 1, 2, 3, 4, 5, 6. And another methyl group over here. Right? So we've got 6 carbons. We have hexane. We have C6. How many hydrogens would that be? 6 times 2, 2n plus 2. Remember, 2 times 6 is 12, 14 hydrogens. So in order to link 2 of the carbons in this to make a ring, what do we have to do first? We actually have to remove 2 hydrogens, right? Because it's already saturated with hydrogens. There's no place for any of these carbons to make another bond. Right, so we have to remove 2 hydrogens, and so I'm going to take 1 off of each end, and because I'm taking it off as an H dot, a hydrogen atom, I'm going to have an electron left over. We're going to have it like this. Alright, so now what we could do is we could take these 2 electrons and we could use them to form a new bond. Alright, and if we do that, we have 6 carbons. We're going to make this into a cyclic structure like this. And because it's still a hexane, but it's in a cycle, we're going to call this cyclohexane. Right, so what's the formula for cyclohexane? Right, so now we have C6. We have how many H's? We have 2 H's on each carbon, and we had to remove 2, so this is H12. Alright, so this loss of 2 hydrogens, so we're removing 2 of them over here, the loss of 2 H's equals what we call an unsaturation, which means that we have less than the maximum number of hydrogens for a given number of carbons. Alright, let's look at some other ring sizes that are possible. So if we have 3 rings, 3 carbons, we can make it into a triangle like this. This is cyclopropane. So all we do is we write cyclo in front of the normal alkane name. We could have 4 carbons, right? This is cyclobutane. 5 would be cyclopentane. Right, we already drew cyclohexane. If we had 7, it would be cycloheptane, cyclooctane, and on up. Alright? So let's take a look at how we would name cycloalkanes. Alright, so most of the rules are going to remain the same. Alright? Except we're going to have the parent is going to be the ring, as long as the ring is the biggest part of the structure. If we have a chain, an alkyl chain, attached to the ring that's bigger than the ring size, then we'll name the ring as a substituent. I'll show you an example of that. Alright, so let's look at the first one. So we have this cyclopentane, right? Cyclopentane. pentane, and we have one group attached. All right, so what is this group called? All right, so we can name this all in the same name. Notice it has the two methyl groups at the end. So this is an iso structure. The whole thing has 4 carbons. This is isobutyl. Okay, so this is isobutyl cyclopentane. All right, so for a ring that has a single substituent, we don't have to put a number out in front, because if we were going to number that, we would automatically put that as the position 1. So by definition, it's at position 1. So no need for a number. On mono-substituted cycloalkanes. All right? Okay, so here's another cycloalkane. So what's going to be the parent of this one? Okay, so this one has a parent. Let's write it up on top. Has 6, right? Cyclohexane. And look at the substituent. This is like this kind of a big substituent here. So for this substituent, we're going to, because it has more than 4 carbons, we're going to name it in a systematic fashion. So remember, when we do this, we count number 1 for the attachment point. So this is a carbon that's attached to the parent. So then we number it out to the end. So 2, 3, 4. So this is a butyl group, and it has this carbon, this methyl group, attached at its position 2. So this is going to be a 2-methyl-butyl, and we'll put that all in parentheses. So that tells us that the methyl is on the 2 position of the butyl and not on the 2 position of the cyclohexane. All right, so if we had another substituent on the ring, we'd have to put another number out in front of the parentheses to tell where this whole group is attached. But because this is only a mono-substituted cycloalkane, we don't need the number out in front. Okay, so the next one, look at, we have a long chain and we have a very small ring. So in this case, the ring is going to be a substituent. And so just like always before, we're going to find the longest alkyl chain. It goes to here. And we're going to number that so the first group gets the lowest possible number. All right, so that means we're going to start numbering here, because then the cyclopropyl group is going to be at position 1. Right? If we number from the other end, then the methyl group is at position 3. So 1, 2, 3, 4, 5, 6, 7. All right, so we have the cyclo. It'll be just like other alkyl groups, right? From methane to methyl, from cyclopropane to cyclopropyl. So we have a cyclopropyl group and we have a methyl group, all attached to a heptane. All right, so here's our heptane parent. Which of those should we put first? Okay, so we're going to put cyclopropyl because we're going to count the cyclo part. C comes before M for methyl. So we're going to have something like 1 cyclopropyl, right? Hyphens between numbers. 5 methyl heptane. Okay? All right. So now let's look at these bottom ones. We have multiple substituents on the cycloalkane rings. Alright, so in these cases, what we're going to do is we're always going to number one of the groups at position 1, and we're going to number it such that the next group we come to gets the lowest possible number. Alright, so for the first one, we have two possibilities. We could either start here with number 1 for the methyl group, and we could count it clockwise like this. Alright, so that would give us a 1 and a 3, the methyl group at 1, and what's this group here? Okay, we could call this an isobutyl group. Alright, and this is a methyl. Okay, or we could start at the other side. 1 for the isobutyl, 2, 3, 4, 5, 6. So which of these numberings do you think we should choose? Well, if we have a tie in our numbering systems, then we're going to choose the group to go first that comes first in the alphabet. All right, so we're going to choose, remember, iso is included in alphabetization, so we're going to put that one first. So we're going to use the numbering in green. So we're going to say 1 isobutyl, and then we have 3 methyl cyclohexane. Okay, so now we have two what we could call tri-substituted cycloalkanes. All right, so again, what we want to do is number it to give us the lowest possible numbers. We want to number we're going to start number 1 at the position where if we number either clockwise or counterclockwise, it gives the second group at the lowest number. All right, so we're going to start numbering right here, because if we number that 1 and we number clockwise, then it puts our second group at position 2. Right? We could number it back the other way, so let's number this on around 4, 5, 6, 7. We could number it here 1, 2, that also puts the second group at position 2, 3, 4, 5, 6. So how do you think we should break this tie? Alright, since we have another substitution we haven't counted yet, we're going to number it so that third substituent gets the lowest possible number. Okay, so in this case, we're going to number it as it's shown in red, because then we have 1, 2, 4 rather than 1, 2, 6. We only use the alphabet if the numbering system is completely tied. Alright, so we have ethyl groups. We have 2 ethyl groups, and we have a methyl group. So ethyl comes before methyl. So we have 1, 2 diethyl, 4 methyl cycloheptane. All right, one more. All right, so we got 3 groups on this one. We can number it in either of 2 ways. Right? If we start here, 1, 2, 3. Right? This gives us the lowest numbering. Or we could number from here, 1, 2, 3. So how the numbering's completely tied here. So how do we break this tie? We break it with the alphabet. So ethyl comes before methyl. Okay, what's this group over here? All right, 3 carbons, not branched at all. This is propyl. All right, so let's put this down here. Okay, so this is a cyclopentane, right? And we are going to, what numbering we're using? The green numbering, right? So the ethyl group comes first. So we have 1 ethyl. We have, what do we list next? 2 propyl, No, we don't list them in order of number, we list them in alphabetical order. So methyl comes before propyl. So 3-methyl, 2-propyl cyclopentane. All right? Easy, straightforward. We're just building a little bit on. All right, so let's just do a couple of these where we're doing it in the reverse order. All right, so remember when we're looking at a name and we are drawing the structure, the first thing we want to do is look at the parent, right? So make sure if you look at pentane, you look to see that this cyclo is out in front of it, right? So we have cyclopentane, 5-membered ring, and we have an isopropyl attached to it. All right, you remember what an isopropyl is? All right, 3 carbons, and it has a branch, 2 methyl groups on the end, so this is just 3 carbons like this. All right, and it doesn't matter whether I attach it to this carbon like I chose, or this one, or this one, or this one, or this one. You can put it on any of those carbons that you want. All right, because we'd always start numbering from, whatever the position of the group is. Even though in this case, because we only have one group, we don't have to put a number. Okay, what about the next one? This is also a cyclopentane. All right, so we got a 1 position, so let's just choose one. I'm going to put 1 here. 1, we got 3 methyl groups, 1 methyl, 2 methyl, 4 methyl. All right, so again, I could start anywhere I want. So I could start over here, 1, and I could go 2, 4. All right, so these two are the same as each other. We just got to rotate it around. All right, so let's I didn't really finish this one down here. Let's make this nonane. Okay, so this one, notice it has cyclopropyl as a substituent. And so this is just a normal alkane with a substituent. It's got 9 carbons, 2, 3, 4, 5, 6, 7, 8, 9. It has cyclohexyl on the 4th, 1, 2, 3, 4, no, on the 6th, 6. So here, and here's our cyclopropyl. Sorry, I keep saying that wrong. So that's at 6, and then 4 is here, and 4,4-dimethyl. So we got 2 methyl groups there. All right. One more, cyclohexane. These hexagons you'll get lots of practice with in this class. 1-ethyl. Okay, I'm just going to put my ethyl right here. I'm going to count it clockwise. 3,3-dimethyl. Oh, is that named right? No, that's not even right, is it? Okay, remember it's about numbering. So we want to number at the group that gives us the lowest second number. So if we number from here, then that actually puts the second group at number 1 as well. So 1, 2, 3. All right, so the correct name here should be 1. No, it's still going to put the ethyl out in front though. 3-ethyl. 1, 1-dimethyl cyclohexane. Remember that this di part here, we don't alphabetize that. Do not alphabetize. All right, so we're alphabetizing M for methyl, so that goes after ethyl. Okay, so now we know how to name these. We've got going on. So let's start to think about the stabilities of these different sizes of rings. Okay, so we have a couple of things that we can consider. One is called the bond angle. Okay, so this is the ideal angle depending upon the hybridization. So in all of these structures, what are the hybridization of all those different carbons? They're all sp3, right? So what's the ideal angle? Should be 109.5. All right, so let's look at what the angles actually are. All right, so in a cyclopentane, what's that angle? Okay, it's only 60 degrees. All right, so the carbon wants to be 109.5, but it's bent all the way down. It's forced all the way down to 60. That creates a lot of strain. Okay, angle strain. It wants to snap back open, but it can't. All right, so what about cyclobutane? All right, so that angle is going to be 90 degrees. It's getting a little better, getting closer to 109.5. And for cyclopentane, this would be 108. So that's getting really close. And then by the time we get to cyclohexane, we've gone on up to 120 degrees. So that seems like that would be starting to create a lot of angle strain as well. So what would we consider these? What would be the trend in stabilities, right? What would we predict? So we would predict that this should be the most stable. And then it's going to get less stable going in each direction, right? Okay, so that's just based upon angle strain. Okay, so the next thing has to do with eclipsed hydrogen. So really, it's not so much the eclipse, but it's the loss. When we have them eclipsed bonds, we have a loss of what we call hyperconjugation. So the more eclipsing we have, the more loss of hyperconjugation that we have. So let's just think about how many eclipsed bonds there are. So if we start out here, right, we have on each one of these, we have two H's. One would be coming out of the plane towards us. The other one would be going back into it, like this. And if we count all of the eclipsing, we'd have 1, we'd have 2, 3, 4, 5, 6. We'd have 6 eclipsed hydrogens. All right, if we go to cyclobutane, we'd have 8. Cyclopentane, we'd have 10. Cyclohexane, we'd have 12. All right, so remember, the more eclipsing that we have, the less hyperconjugation. All right, so that means that this should get more stable going to this side. It has less eclipsing, should have more hyperconjugation. All right, so from this, we would probably think the most stable ring had to be somewhere in the middle in here, right? Because we want to have less eclipsing, but we want to have a bond angle that's near 108. Okay? So, when we go through this whole rationale, what are we assuming? Okay, we're making an assumption when we do this whole analysis here. All right? Can you come up with it? Okay, the thing that we're assuming in here is that each of these rings are actually planar. As they're drawn, right? Think that's true? No, it's not true. In fact, these rings can bend, except for cyclopentane, propane, right? There's only three carbons there, but all of the other rings can bend out of the plane to help reduce both angle strain and to maximize hyperconjugation. All right, so in the next video, what we're going to do is we are going to talk about conformations of cycloalkanes, and particularly we're going to talk about cyclohexane because that's a very common ring size and it's the size where the conformations are most clearly described.